Welcome to solverfy.
All right, so problem number 50 series of reactions, and they, if they're possible, and if they're not possible, then why? So let's start with A. So A is a minus pion plus a proton collide and form a neutral cation plus a proton plus a neutral pion. All right, so we need to just look at all of our conservation laws, and as long as conservation laws are conserved, then they're possible. So first, let's start with charge. So we have -1 for a minus pion, +1 for a proton is equal to 0 for a neutral cation, +1 for a proton, +0 for a neutral pion. So -1 + 1 is 0, does not equal 1, so this is not conserved. So this is forbidden. And it's forbidden because charge is not conserved. All right, so for B gives us a negative cation plus a proton. We collide and forms a neutral lambda plus a neutral pion. So let's look at charge. We have -1 plus 1 is equal to 0 plus 0. So -1 plus 1 is 0, 0 plus 0 is 0, so that's conserved. Now let's look at baryon number. So baryon number, you have, so the cation is not a baryon, so it's 0, plus 1 for the proton, which is a baryon, is equal to 1 for the lambda, neutral lambda, plus 0 for the pion, which is not a baryon, so that's also conserved. Let's look at lepton number. So lepton number, none of these are leptons. Okay, so that's conserved. Now let's look at spin, because spin also has to be conserved. It's conservation of momentum. So we have 0 spin for the cation, plus 1/2 spin for the proton is equal to 1/2 spin for the lambda baryon, and plus 0 for the pion. So that's conserved. Now let's look at strangeness. All right, so for strangeness, we have -1 for the negative cation, plus 0 for the proton is equal to -1 for the neutral lambda, plus 0 for the pion. So that's also conserved. So this product, as long as there's enough kinetic energy for this reaction to occur, this collision reaction is possible. Possible. All right, so let's create a new page here. So for C, we have a positive cation plus a neutron collide and form a positive sigma plus a neutral pion plus a photon. All right, so now let's look at our conservation laws. Charge, we have 1 plus 0 is equal to 1 plus 0 plus 0, so that's conserved. We have baryon number. Baryon number is 0 for the cation plus 1 for the neutron is equal to 1 for the sigma plus 0 for the pion and 0 for the photon, so that's conserved. Let's look at spin. So for spin, we have 0 for the cation plus 1/2 for the neutron is equal to 1/2. Sorry, minus 1/2 for the sigma, plus 0 for the pion, plus 1 for the photon, because photons have a spin. So 1/2 is equal to 1/2, so that's also conserved. Let's look at lepton number. None of these are leptons, so 0 plus 0 is equal to 0 plus 0 plus 0. It's supposed to be 0, so that's also conserved. Now let's look at strangeness. So for strangeness, we have 1 for the chion plus 0 is equal to minus 1, because that's an antiparticle, or minus 1 for the sigma, plus 0 plus 0. So this is not conserved. So this, because strangeness is not conserved, it is forbidden with the strong force, but allowed still through the weak force. So I should say possible with the weak force. Okay, so now moving on to D. So for D, we're given a positive chion decays into a pi meson plus a neutral pion plus a positive pion. All right, so let's look at charge. So charge, we have 1 is equal to 0 plus 0 plus 1. And then let's look at the baryon number. We have, none of these are baryons, so 0 plus 0 plus 0 plus 0. Sorry, 0 is equal to 0 plus 0 plus 0. Lepton number. None of these are leptons, so 0 plus 0 plus 0, so that's conserved. Let's look at spin. You have 0 is equal to 0 plus 0, so that's also conserved. Now let's look at strangeness. So with strangeness, we have 1 for the chion is equal to 0 plus 0 plus 0, because pions do not have any strangeness, so this is not conserved. So it's forbidden via the strong force, but still possible via the weak force. So forbidden with strong force, but possible with weak force. Okay, so finally the last one, E. We have the pion, a positive pion decays into a positron and an electron neutrino. So let's look at charge. 1 is equal to 1 plus 0, so that's conserved. The baryon number. So that's 0 is equal to 0 plus 0, so that's also conserved. They're not baryons. Lepton number. We have 0 is equal to minus 1, sorry, plus 1, because that's a positron, so it's minus 1. So that's conserved. Spin, we have 0 is equal to minus 1/2 spin for the positron, plus 1/2 spin for the neutrino, electron neutrino, so that is conserved. Now we have strangeness. So strangeness is 0 plus, where was I? 0 is equal to 0 plus 0. So that's also conserved. And then conservation of energy. Mass, energy. So you can already tell that's conserved because the pion has much more mass than an electron. But we'll go ahead and write these down. So the pion is going to be 139.6 MeV minus an electron, which is 0.51 MeV, which is minus 0 because a neutrino has no mass. Basically has no mass. It has very, very little mass. But this is basically approximately equal to 139.1 MeV. Now, so energy is conserved, but so the neutrino and the electron, the electrons of the neutrino, so this is mediated by this kind of reaction would be mediated by the weak force. If you look at table 2, it does not, it's not mediated by the strong force at all, so this would be possible via the weak force. All right, so that was it.